Hi, good morning. Um, Hi, good morning. So let's get started. So how was the last exam? I haven't seen it yet, so I haven't graded them yet. I'll probably hand them out on Wednesday. Um, and at least one of you wanted the extension, so I'm not giving the answer keys till Wednesday too, right? So hopefully the homework, the exam was not too hard, right? Um, yeah, pass the. So you should have the next homework assignment and project, and if you had a chance to look at it, it's so like I mentioned before, we are almost done with most of the main issues that we need to cover in this class. There are. I'll edit you out if you show up. Right? So most of the interesting stuff we already covered. We need to cover something with IO systems. We didn't do it in the last module, and we need to look at the protection and security and stuff. But I made a conscious effort not to touch the distributed systems because that's a whole big topic, and I would rather make sure that we understand all the stuff we did so far, right? The basic fundamental operating systems. So on that vein, the next homework project, I want you to look at a machine, try to see what kind of stuff they have. What's the processor? What's the device? How it was partitioned and stuff like that, right? And I want you to show me two proofs that you are right. Like report why you think it's doing something, and then another reason why you think it's exactly what it is, right? So you could say, like I looked at the book and give me the page number or something that you looked at. You can say you looked at the source code, what is it that you saw, right? So there's a whole bunch of stuff, and I'm leaving it up to you to figure out how much you learn of the stuff but I want you to look at some machine, right? So you can use the machines in the lab, or you can use any machine that you have. I prefer Linux or Mac or one of those things where you can get the source code to the operating system. Right? If you want to do it in Windows, come and talk to me so we can make sure that you have enough material to back up something. Right? I don't want you to say, I think it does this, but I have no way of proving or no way of looking it up. Right? So is that clear? So hopefully it'll be easier in some sense. But it builds up to some of the stuff that I want to do after we finish the book chapters, which is try to figure out how you would design operating system for the different machines and stuff. So far we talked about what are the trade-offs in certain policy, and we'll see how you do that for certain kind of stuff. Does that make sense? Right. So today I want to finish up with the IO systems, right? So do you have any questions so far with the file systems? And hopefully the project was helpful in trying to keep some of these things in perspective, right? So the notion of IO systems, that we cover here is how do you do IO, right? So the first thing one of the things we looked at was what are the different kinds of disks and drivers and stuff, and how do they how the disk organize sectors and tracks and all those things. And then we looked at how you would build file systems and directories and stuff on top of those disks. What this talks about is how does the operating system interact with the input-output systems, right? And as you may have imagined, there's a whole lot of different input-output systems, right? You have the disk, and if you ever bought a disk, you hear people talk about SCSI or ATA, serial ATA, Firewire, USB, and so on and so forth. There are different kinds of devices. There's a printer, there's your keyboard, your mouse, and your screen, and all those things. And each have different way they interact, right? So for example, your screen is typically an output-only device. Whatever you write shows up on the screen. You rarely read something from the screen. And your keyboard is usually input-only device. There's nothing sent to the keyboard, and so on and so forth. And there are different ways of how they could be plugged in together, right? So if you've seen a FireWire hard drive, right? You can chain them together back to back. So each unit will have 2 ports. You connect one to the computer, you can connect another hard disk to that, and you can keep chaining them. And you can do that with the SCSI hard drive and stuff. So how many of you have external hard drive which is FireWire? Okay. So in the FireWire, you would do something like that. I noticed some of you said you have external hard drive, right? Somebody else. What is yours?
USB.
USB. So if you use USB, then you hook up, the drive directly to the port. But you can buy little external hubs where you can connect the hub to the computer and then many devices to that hub, right? And depending on the kind of devices that you have, they can either do direct I/O instructions or memory mapped I/O, right? In direct I/O instructions, processor itself, I mean, you won't notice that as a user, but essentially, your operating system would initiate I/O by calling special instruction, right? And that depends on the hardware. And memory mapped I/O, over the memory map files, right? So essentially, the OS would set things up such that if you write into that chunk of memory, then that goes into that controls the hardware, right? So you can essentially say, if you write something into 100, memory address 100, then the disk driver would read that contents. And disk driver would write its contents into that memory. So from your process, from the OS perspective, it looks like a chunk of memory, but it's actually mapped into the hard drive. So anything you write in here goes to the store, the I/O device. Anything the I/O device writes will show up on the memory. Right. So here's a view of a typical machine that's in your book. I hope you can see it from the back, right? So there's usually a bus, which all these I/O devices hang off of, PCI or something like that, right? And you have a SCSI controller which attaches to SCSI disks and SCSI kind of things. SCSI stands for Small Computer System Interface. And essentially, you can have a certain number of disks hanging off of it. And most of us, on a desktop would tend to use a IDE disk controller, which is on the lower left corner, right? Where you can connect 2 hard disks to each controller. And you have a graphics controller showing connected to your monitor, and you have other controller, parallel serial ports and so on. So depending on what's the data rate, depending on how much you expect it to affect the operating system, you tend to do the I/O differently, right? So there are 3 different ways of doing this, and we'll go through each one of them. So the idea here is, if there is something that needs to be set to the OS, right? So let's say the disk on the IDE controller has some data that it wants to give the operating system. You'll give that to the IDE disk controller, right? And the disk controller has to somehow give it to the operating system, right? And we're trying to see how that would happen. The first way you do that is through polling, right? Essentially, the OS sits there and checks every so often to see if there is something to be read. So every so often, it'll go in a loop and say, "Ask IDE controller, do you have something to read?" And if it has, it'll read it. If not, it'll go on, right? So polling is simple. It's sort of like a busy wait for the I/O, right? So you can either go in a while loop, or you can wake up every so often and ask the device, right? So what would be a bad thing about doing polling? What is the condition where polling would work? What is the condition where polling would be a terrible idea? Give me a situation where polling would be good. Just would polling be good if you expect lots of I/O or very little I/O?
So a little bit.
Polling would be good, you think, if it's very little I/O?
It won't interrupt the OS too much. If you have transferring huge files, interrupting the OS almost constantly, then it's not going to really get anything done, or it just might slow it down.
So you think that polling would be good for Blue line.
But yeah, that's frequently used, so it's just.
Do you have opposing view? So polling essentially, you have the processor, the CPU, just actually the OS every so often go and check to see if there's a data, right? Actually, it's the opposite, right? So it's opposite because, so his answer was, if you have little data, polling would be useful, right? So if you want to read all the contents, right? If you have only little stuff, then essentially, say if I poll something 10,000 times, right? So if you only have data for the 1,000 times, the rest of the 9,000 times I'm just waste myself asking, right? It's not like a one-to-one kind of thing, but usually, if I have to keep asking and there's nothing, right, then it's a waste for me, right? In that case, I would like to be interrupted. We haven't seen what an interrupted would be. So think of this as like nagging, right? If somebody keeps asking you, do you have something for me? Do you have something for me? Do you have something for me? If you have something all the time, then there's a good way to essentially keep going, right? But otherwise, most of the time if there's nothing, then polling may be bad, right? The other way to do that, so typically if there's not enough I/O, then you prefer interrupt driven. So where the OS will schedule something to the driver, and if there is something to be read or what have you, the device will interrupt the CPU, right? So the processor does not have to wait for I/O. So it knows that when there is I/O, it will be interrupted. So it can go on to do other stuff till it gets interrupted, right? So the traditional assumption is, if there's rare data items, then interrupt is a good thing, right? Does that make sense?
Yeah, that makes sense.
So if you don't have a lot of stuff, then essentially the processor can do other stuff, and when there's a data item, then it will interrupt, right? And when you have interrupt, you need to have interrupt levels, because otherwise, if all interrupts are equal, then all the I/O devices will interrupt equally, right? And some I/O devices may not be as important as others, right? For example, if your keyboard and your disk is interrupting, you may choose to ignore a keyboard interrupt and be able to read the disk interrupt, right? Because disk is. So it also depends on what the disk controller is willing to do if you don't respond back, right? So if the disk controller says, I have a data block for you to read, and if the OS ignores it for a long time, right, it may just throw what it read because it doesn't have enough space or what have you, right? So depending on that, you have different levels of interrupt, and also you have non-maskable interrupts, meaning these kind of interrupts cannot be interrupted. So if you're reading a disk I/O, then you can block all the other interrupts. So depending on what the device is and how it's doing, you get to choose the priority of how you want to deal with them, and with something very important, you stop all other interrupts, right? So for example, your power button has a much higher interrupt rating than anything else, right? You can check that if you take your PC and try to do the reset button, right? Not the reset button which is not interrupted at all. Like some PCs, if you press the reset button, it just resets the machine. But some other machines, you'll see a prompt saying, your machine is going to shut down because you press the power button, and that interrupt has much higher priority because something is catastrophically going wrong, right? If it has ways to figure out that the power went off, that is usually catastrophic. So it'll stop everything else and try to operate it first, right? Mouse interrupts are usually not that critical, because if you lose a mouse something, I mean your mouse doesn't move smoothly, but it's still okay, right? So essentially, your OS is chugging along, and when it gets an interrupt, right, your instruction will be interrupted because it comes in as a hardware interrupt. You go to the interrupt handler, you do what you have to do to read the object or write what, take care of the interrupt, and then come back and keep going, right? So while you're doing the I/O, it could be an input, or it could be an output, or it could be error, right? The printer is out of a paper, your disk is crashing, or what have you. And you process those, and then you come back, right? And therein lies the problem with if you have lots of interrupts. If you have lots of interrupts, then essentially you may not make any progress at all in your application. You're just spending all the time trying to take care of the I/O, right? And this brings up a notion of priority, because interrupts are happening at a higher priority. So if you have a normal user process, when you get an interrupt, it goes to the kernel decides that this has to be taken care of immediately. It reads the stuff while you're sitting there and in a lower priority task, not making much progress, right? Some of you might have noticed this. If you're trying to do a lot of disk I/O, if you're doing lots of swapping and stuff, your machine will be practically useless while it's doing a whole bunch of stuff. Your disk will go crazy. Something is going on, except you can't get anywhere, right? The only thing you can do is press the power button, and depending on the operating system, it'll prompt something saying, do you want to do something? But as a normal process, you can't really do anything, right? So if you compare polling and interrupt processing, if you're getting lots of interrupts, and you're essentially going to keep doing this, save the state from application process, go to the interrupt handler, do what I have to do, then come back, then go back to interrupt handler, and so on. And that's the reason why you prefer polling in this condition. Because polling, it says the OS decides that now I want to do I/O. There's no interrupt here. Now I want to do I/O. It goes into the interrupt on the I/O routine. It can read however much I/O it wants to read, right? Usually it will want to read all the I/O, but it can choose how much it wants to do before coming back to the user process, because it's not being interrupted, right? So every so often it has to go and read the contents, and if it wants to do it once every second, then whatever it wants to read is what it wants to read. So it has more control if you do polling. Whereas interrupt, you don't have much control, because even if the OS does not want to read anything, it'll get interrupted, it'll have to go to the interrupt routine, and then it'll decide, okay, I don't want to deal with this interrupt, and it goes back, right? So when you look at different operating systems, right, the real high performance operating systems will tend to go between both these models. If you're doing lots of I/O, you'll tend to go into a polling mode. If you're doing less I/O, you'll go back to interrupt mode, just to have a balance, of whether how much control it has, how much I/O it wants to do. Right. So once you have this notion of a polling or interrupt driven processing, the next problem you need to solve is, what is the role of the CPU in all this stuff, right? So assume that you have to use memory mapped I/O or special I/O instructions, right? Which essentially says that if I want to write something to a disk controller, I have to write either into a memory location or perform some I/O instructions, right? And then you have the interrupt or poll processing. So with all this stuff, what it essentially means is, if I want to do I/O in poll mode, right, the OS decides that every so often it'll do I/O, right? It'll poll the device to see if there has to be some I/O, if it has to be read something or return something. And if it has to be done, it has to do this instruction. It has to either do a I/O instruction or memory mapped I/O, right? Which essentially means that it has to, say the I/O device lets you read in bytes, right? And I want to write 4K byte. I have to write one byte at a time using a input output instruction, right? So for example, if I have the I/O instruction, this is the I/O instruction given by a machine, right? And we can write a byte, right? So if I want to write 8K block, right, I have to essentially do for I have to sit and do this loop, right? Because I/O essentially means that I need to do I/O at the rate that the device can read. So if I have to do 8K I/Os, then I have to do an instruction like this, right? And input output is typically slow. I mean, the CPU is much faster than your printer or what have you, right? So your CPU can sit for a while trying to do this. You can do this IO instruction, and these are all slow. So essentially, it's sitting here doing a very slow operations for a long time, right? So your machine can be extremely slow because it's trying to do the input-output. So to solve the problem, we have a notion of a DMA, right? What it essentially does is the IO is processed by a separate chip, right? You can think of this as a IO CPU, right? Essentially, you can program this chip to only do IO. You can program it to do this loop without actually working on the operating system, right? So now we have the main CPU, right? Let's say this is the main CPU, and now it has the support of a little IO controller, right? Which is sort of like a CPU, except it only does input-output. So if it has to do this loop, it can say, do this loop over here, right? Essentially, it can say, I want this is a chunk of memory. I want this to be sent to the disk drive. So this controller, right? I want you to write from this memory location to this memory location to this IO device. And when you're done, you can interrupt back to me, right? So this can do polling or anything over here, but after it's done, it'll interrupt back saying it's finished, right? And that's the idea behind DMA. So if you were to do this within the CPU, your processor will be slowed down. So now you're offloading some of the stuff into another processor, right? And this goes way back. I mean, like when we started out in the mainframe world in 60s and 70s, there used to be lots of little controllers around the main processor, right? Input-output was taken care of by different processors because there was printers and the card punch readers and stuff like that. And as we went into the PC world, everything began to go into one CPU, right? So the first IBM PCs and all, the processor used to do a lot more. Now we are beginning to offload some of the stuff back. So you have a DMA controller to do direct memory, the memory access thing. You have other controllers. Can you think of another controller that you heard of or you used, which does some processing for you? This one controller that, if you're into games, you probably would have you heard of it because that's the one which gives your machine good stuff. Okay. Yeah.
GPU.
Yeah. Your graphics controller, right? Graphics controller essentially does the same thing, right? Your CPU can do all the stuff that your GPU can do, right? Your CPU. So essentially, when you're doing graphics, right? This is not a graphics class, but there are primitives that can be done, right? So you can either draw all kind of dots to make a pattern, right? Or you can have it draw lines, or you can make it draw, more complicated shapes, right? So let's look at drawing a line, right? Drawing a line it's simple math. I mean, it's your simple geometry going through and drawing these lines. Essentially, you have to go from here, figure out all these points, and do the calculations to draw that line, right? And you can think about shading and all those things, all of which can be done by the CPU, right? So if it has to do it at the game rate, your 30 or 60 frames per second, right? Your processor has to be extremely fast to keep up with this kind of stuff, right? So you offload that into this graphics processor, which is much faster than your main processor, but it can only do the graphics operations very quickly, right? So essentially, you offload it into the graphics processor. So instead of saying draw a point, now you can say draw a line. Now you can say complex structures, right? And essentially, it goes up and does all the stuff, right? So the GPU is not needed, but if you want any kind of performance, you have to offload it into that particular stuff, right? And you has anyone heard of another?
Like you have audio controllers, and some LAN controllers have CPUs for encryption.
Yeah, I mean, any reasonable system has all kind of other controllers, right? Audio, you can either do it by the CPU or you can have a audio controller. LAN, you can do it through the CPU, or you can offload it, right? So if you bought like IBM laptops or many of the cheaper laptops, right? Cheaper laptops tend to push everything into the CPU, and a little bit more expensive can afford to have these hardware, right? So in the cheaper laptops, you might have noticed that if you're doing listening to audio, right? When the CPU is busy, it'll stop, right? If you have a little bit more expensive stuff, then the CPU would not affect the performance, right? You might have seen that with your dial-up modem. Most of the cheaper laptops tend to have a dial-up modem which is built in through software, essentially run by the main CPU. Your audio run by software, right? There are some things you can't do. You can't run a gigabits per second Ethernet out of CPU. Or rather, you can run it and you cannot do anything else. So those you need a controller. And same for SCSI. If you have lots of data volume, then it's better to offload them, right? And if you expect only a few bytes, then the CPU can still process them, right? Your mouse can still be operated by your main processor because people rarely move the mouse very fast, right? It's you just physically have to move it. Whereas all this other stuff. So, and that's one of the things I want you to look for your the next homework project. Try to see what your machine has, right? So, actually, if I go back to the so in this case, the graphics controller, for the gaming stuff, it's so powerful. It's actually a separate supercomputer sitting off of there and doing all kind of stuff. And the main processor only tells it little high-level stuff. You can say, draw a sphere up here, and the real stuff happens between the graphics controller and the monitor, right? And some other graphics controller that you can buy off the shelf right now is extremely fast, right? And some people who try to actually let the graphics controller do some mathematical processing for themselves, but those are. How many of you have seen a graphics controller, like some of the high-end graphics controller? It'll have its own fan, and it's kind of quite bulky. It's not a small little thing, right? But your cheap desktop will have the graphics controller built into your motherboard, a small little one. Right. So the way, so when you use DMA, right? When the device interrupts the CPU to say that there's some operations to be done, right? The OS gets interrupt from the device controller, right? So it has to figure out what it has to do. So it has to figure out whether if something has to be read, it has to figure out that the disk is saying that something has to be read. It has to allocate the right memory, right? So for the data to be read, right? It has to make sure that all the protections are done, because at the device level, they don't have notion of protection. They can read anywhere. They don't really care where it has to be read, right? So you have to make sure that this read belongs to the right process. Set the pages up so that everything is good, right? So you find out that this memory page does belong, should be where the object should be read. Tell the DMA controller that you have to read X amount of bytes from this device driver, from this disk onto this memory, right? And then the processor and then the CPU just goes off, right? Because it knows that the DMA controller would do all the stuff, and when it's done, it'll get an interrupt back saying, I finished that I/O that you asked me to do, and then you can proceed, right? Is there a step I skipped in the middle? Would that be enough? They said disk, right? So I tell the DMA controller that they said stuff from the disk should go in here, right? And this, I know that this page belongs to process P1, and I initiate this transfer, and then I go off. Think of what would happen with page replacement. And it's been a little while back, right? So what would happen with page replacement with that page? So when you do you remember when you do the swapping, right? If you see a page, if it's not being used for a while, you send it off to swap disk, right? You do least recently used and all kind of policies to figure out least recently used pages are sent to the swap space, right? You can be guaranteed that nobody is touching the page from the OS perspective because I/O hasn't finished, right? If you're reading something from the disk, no process would be able to read that page because it's still halfway through and you can't so that process is waiting, right? So what would happen if you don't do anything special? Yeah.
Then it could get moved, or the OS could attempt to move it to disk if it's not locked, and then the DMA controller might write to an invalid, something that another program, another data that you don't want overwritten.
Yeah, because DMA controller knows nothing about processes or anything. It doesn't know anything processes or pages or anything. So all it knows is I have to read something from the disk, from this whatever is coming here to this memory page, right? It has no notion of who this belongs to and stuff. So if the OS comes around and says, okay, this page is not being used, so I'm going to put this into swap, right? Fine, you can do whatever with this. You can schedule something with the swap. And then if you assign a new process, right? The DMA controller doesn't know about all this stuff, so it'll keep writing back. So half your page will be from the other process, and half will be from a different thing, right? It'll just keep overwriting into memory because DMA controller does not talk back with the OS, right? So you need to lock this memory page, right? Lock meaning that OS would know that this page cannot be used for anybody else till the IO is finished. This page cannot be moved. This is off limits for itself, right? So again, if you go back to your Linux or whatever to look at the amount of memory allocated to your process, right? You'll notice that it will say certain amount of pages are being used for something, certain amount is free, and it'll say 1 meg is locked, right? Essentially, it says like this cannot be moved. Don't touch it, because if you do, then the whole thing will fail because the DMA controller does not know anything about that. And so essentially, by doing this, the DMA controller can, the OS offloads this stuff, and DMA controllers can be extremely much more complicated than what I mentioned here, right? They can do what is called scatter gather. It's not in your, I don't think it's in your book, right? So essentially what it can do is, it does not have to say this read the one memory page. It can actually say, read this whole disk, right? And put it into 3 little chunks. You can say for the first so many bytes, write it here, second so many bytes, write it here, third so many bytes, write it here, right? Or if it has to send it out, it can say, send it out by reading a whole bunch of bytes all over the place and then send it out, right? It can scatter what it reads across multiple different pages, or it can gather multiple different pages and write it out, right? So DMA control does not have to be a simple, you write this block kind of thing. You can say, collect a whole bunch of stuff, write it out, or read a whole bunch of stuff and scatter it all over the place. So having a DMA controller can really help you. In fact, if you're doing any kind of like serious I/O, if you're doing like SCSI and all those things, you want to do DMA for performance, right? Because this way, your main CPU can still do something else, but not have to worry about that. So one of the things you want to find out is how many of your desktops actually do DMA, right? And many of your desktops may not actually have a DMA controller or a good enough DMA controller to do scatter gather or many other stuff, right? Why is that? Suppose your laptop has no DMA controller, right? Why is that acceptable? Why do they think it's okay?
This is how you're not going to be doing like high performance tasks on a battery driven laptop.
Yeah, there are different arguments. I don't know what the right answer is, right? So one of the argument is you're not going to do high performance stuff, so why bother, right? The other argument I've heard is you can only do only one thing, right? It's going to be one user sitting in front of the disk. So you start PowerPoint, it has to read stuff from the disk, right? And PowerPoint application. So essentially, if you don't have DMA controller, your system will freeze while it's trying to do the I/O to read the program, right? If it doesn't freeze, what else are you going to do? Like move your mouse, right? Because it's only a laptop, so there's not a whole lot you can do otherwise while you're doing this I/O kind of thing, right? Of course, the whole thing is dependent on cost, right? The cost of adding a DMA controller is not that much, but it's still not zero. So, you worry about those costs. And there's also cost with the operating system, because operating system now has to be a little bit more complicated, right? It has to know about locking down the pages. It has to know like scatter gather, and now it'll get two kind of interrupts, right? It'll get one interrupt from the disk saying initiate a DMA, and it'll get another interrupt from the DMA controller saying the I/O is finished. It has to figure out what happened and all those things. And some of the initial OSs or drivers don't really do this, right? So, even if your disk can do DMA, your system may end up in a programmed I/O because it's easier. The first model is called programmed I/O because it's a little program going through in a loop trying to read do the I/O, right? So there are a number of different ways of doing I/O depending on the kinds of devices you have, right? So the one of the two accesses are character stream or stream processing mode or block stuff, right? So if you're reading your keyboard and stuff, it's a character stream mode because it comes as one character at a time. Whereas block is something that you do when you do a disk I/O. You can't read 1 byte. You get the whole block. You can use one byte, but you're going to do I/O in blocks, whereas screens are typically character oriented. Okay? So depending on the type of device, right, you'll do the I/O a certain way. Right? Not all screens are character oriented either. How many of you used IBM old 3270 terminal, IBM mainframe stuff?
I've seen one.
Have you used it?
No.
Okay, so if you've seen them, you might have used it without actually knowing it, like others, if you use some legacy systems, right? So essentially, you'll bring up a whole screen which will look like a form. You can fill out your name and all those, like usually you would have seen it in like DMV or something, right? So you enter something, you can edit everything, and at the usually you'll have something like a send key or something, right? So essentially, when you do a send, it'll send the whole stuff, right? So in the mainframe world, you're doing a similar kind of processing, right? If you do a character-based system, every time you type in a character, the OS has to be interrupted. You have to do something. If you're a mainframe and you're supporting tens of thousands of clients, so you let the terminal itself collect all the stuff. So if you're doing editing, if you're doing deletion and all those things, the OS would never know about it. So you do all the processing locally, and then you press a send, in which case the whole screen is sent, not the local editing, right? Your typical your workstations, you don't do that. You kind of every keystroke, every mouse move goes to OS and it does something and it brings it back, right? So how many of you used a Silicon Graphics or high-end workstation? Not like So if you notice those, right? If you ever get a chance to look at like a very high-end desktop, right? Try to move the mouse on those things, right? You'll notice the mouse will be moving extremely smoothly. You'll be able to see every you've seen moving mouses in stuff like this, right? On a desktop like this, right? If you move it very fast, you'll basically see somewhat, and then it kind of jumps over to the new location, right? How many of you noticed that? I can actually show that, right? So if I do the mouse like this, right, you don't see a smooth motion because you see it kind of jumping around. Do you think it's jumping around? Right. And that's because every time I move the mouse, there's interrupt goes to the OS. It has to do something. It has to redraw the mouse at the new location and then come back, right? And it'll probably skip some interrupts because I'm moving it too fast, because it doesn't think that mouses should be moved that fast, right? So it's kind of okay for this stuff. But the high-end workstations have a mouse driver which does the mouse processing, right? So when you move the mouse like this, it'll be extremely smooth. So it can actually, if you see it, it's pretty smooth, because so you have one controller whose job in life is to control the mouse, right? So you can move it however fast you want, and it'll still keep up with it, right? And I mean, of course, those machines cost 50, 100 plus K, right? So, and so the next mode of operation is the sequential or random, right? And we talked about this before in terms of tapes and stuff. So if you have a tape unit, then it's essentially sequential by nature, because the tape kind of moves across a certain way. If it's a disk or something, it's random access, right? And same for keystrokes. Keystrokes are sequential access. You can't just randomly go to the fifth cat or what have you. The device may be shareable or dedicated, right? Tape units are typically dedicated, because once you have to get control of the disk, then you can move it forward and backwards, because it's not essentially random access. So it doesn't make sense to have two processors read the same tape, because you're reading essentially wherever the last head was. So if two processors read the same tape, then they both get undefined results, right? The speed of operation drives what you do. And I was kind of showing up here, right? Your mouse is a certain speed, so the OS reacts to it a certain way, and I/O happens to it a certain way. If you have gigabit Ethernet here, data is coming at 1 billion bits every second, and you better do something different than the mouse, which is happening at few bits per second. And again, whether it's read, write, or what is the mode allowable for a disk for the I/O defines what you can do with them, right? And so here's a softer view of how the system works. So essentially, you have the kernel has the I/O subsystem, right? So it has a notion. So you would have heard of the device driver frequently, right? So essentially, a device driver is a part of the kernel which talks to the hardware equivalent or the device controller, right? So if I want to say, affect the SCSI devices, the kernel would talk to the device driver, which would talk to the particular device controller. And there are many different device controllers. So if you ever bought one of these things, you would notice that there are different makes and models and stuff. So you would find out what device controller you have, and you have to find the corresponding driver which knows how to talk to that particular controller. And then the OS has to know how to talk to that particular device driver, and you get what you want. Right? And this table kind of tells you the different kinds of operations we looked at before, right? Essentially, like if it's scatter mode or block mode and so on, and what are the different kinds of devices which operate on that model. And you need to know whether it's a block level or scatter level, because what you do after that depends on that, right? If you want to build a file system, you can't build a file system on top of a scatter mode device, because you can't. It's not random access, and it doesn't do all the indexing structure and stuff good, right? So scatter mode devices are typically terminals and stuff, so they are good for input output, like a screen input output kind of stuff, but not for building a file system. And I'm going to go through some of these stuff fairly quickly, and these are more of a programming stuff, right? So depending on how the OS, what the abstraction OS gives in terms of I/O, right? You can either have blocking I/O, non-blocking I/O, or asynchronous I/O, right? In blocking I/O, you do a system call, say for read. In a blocking I/O mode, the call is not released till the data is available to read. So if you say I want to read 4 bytes, your process essentially stops till that I/O finishes, right? In non-blocking I/O mode, right, it essentially says that your system your process will make the call. If there's anything to be read, you will read it. If there's something to be read, it'll return back to you, right? And it's up to you to poll. It's up to you to do whatever to come back and ask for the right contents. So blocking and non-blocking differ in terms of what happens when you come in for reading something and the object is there or not, right? The asynchronous I/O is a lot more complex, and many of you may not have used asynchronous I/O, right? In asynchronous I/O, you can do sort of like what this DMA controller does. You can tell the machine, I want some data to be read, right? So I want to read in this file, let's say from a current location for another 1K. I want it to be written into this memory, right? And essentially, when it's done, you'll get an interrupt or you get a signal, right? Saying, for the application. So this is the way for the application to interleave I/O. So you can schedule all this I/O. It goes up, and when it's done, you'll get an interrupt back, right? So it's pretty good because now you don't have to wait for I/O to finish. You can start a lot of I/O, but then you have to keep track of which I/O you're doing, when it finishes, and all those things. So higher performance applications will actually tend to do that. For normal applications, these are very annoying, right? Because the idea is most of the times you don't have anything else to do, so you're fine, right? How many of you actually used a asynchronous I/O system call? I thought somebody said they used it. But anyway, it's there, and it is for high performance systems, right? So essentially, if you do a asynchronous I/O, it initiates the I/O transfer and then returns control back to you, right? Without having to actually wait for the I/O to finish. And you'll be notified later when the I/O actually finishes. So there are a few more stuff. So then the kernel has to figure out when to schedule the I/Os. It has to do some sort of buffering because some of the devices are slow. So it reads all the stuff, it keeps them in some buffer, and then gives it out to the application, right? So from the I/O device, it has to come into the kernel structure, and then from the buffer, it goes to the user process. So there's copying involved, right? And so you have to balance this notion of copying and with the notion of what should happen on the application, right? So if I have to lock the process and stuff, right, memory for the process, if I don't like that, I can always read it into a kernel data structure, which I always have it locked. And then when the I/O is done, I can copy it from the kernel data structure to the user process fairly quickly, right? And that may solve some problems. So one of the other problems with this model is if you try to kill the process, you can't kill the process, right? If you have the memory page locked for it because it's trying to do a DMA, the process cannot be killed because if it goes away, then the DMA controller is still doing its task, right? You don't usually have a way to cancel the request and stuff. So to solve the problem, you read it into a kernel, and then you can copy it from the kernel to the user process when it's done. It's a little bit more flexible, but it's not high performance because you still have to copy it back and forth within the memory. So some of the other stuff you want to do to get good performance is caching, spooling. If you can buffer all the output and then send it out when you get a change, and allow the application to reserve devices. And once you do that, it's no longer shared, and so you have to worry about deadlocks and stuff. So I'm going to go through. I'm going to just skip these things because we talked about it in different contexts in different systems, right? And I'm going to go to the last page. So to improve performance, which is what you really care about, right? You have to do different things, and copying is something that you want to avoid. You don't want to even copy stuff within memory. So a lot of stuff in OS research tries to avoid extra copies, right? You don't want to copy from the disk to the disk controller, from disk controller to kernel to application process. It's not that slow as the I/O device, but it's still slow. So you want to avoid those, right? And that's why you have some of this scatter gathering stuff where you don't have to. So you need to have fine locking mechanisms in the memory. You need to be able to read stuff back and forth from DMA controller. So the more expensive DMA controllers can do a lot of this stuff, but they're expensive. And that's some of the stuff that you need to do to get performance. Cache some of the stuff, avoid copying as much as possible, and use this different stuff to balance the things. And that should wrap up the I/O systems, and we'll continue with the protection on Wednesday.